Perfect.
All right.
Okay. So my name is Ilinca,
And my name is Beatrix.
and this presentation is about our project and our experience this summer as high school interns here at ISB. So my name, like I said, is Ilinca. I go to Eastlake High School in Sammamish, Washington. In my free time, I love playing with my dog, Pebble. I love reading, and I love to play volleyball.
And my name is Beatrix. I go to Franklin High School in South Seattle. And in my free time, I play soccer and lacrosse, and I also hang out with my dog, Tucker.
So the first thing that we're going to go over is what are diatoms. Justin already talked a little bit about this, but we're just going to go over it one more time. So it's a unicellular microalgae that's been around for millions of years, and it's experienced a large variety of high and low carbon conditions. It's experienced like over 6 times as high as the carbon conditions that we have right now, and also significantly lower. So what we're looking at is kind of like what diatoms are going to look like in the future, like which ones are going to be more and less prominent as carbon conditions increase in carbon. So we're not really worried about like, are the diatoms going to survive? We're just worried, we're just trying to figure out which ones are going to be more and less prominent in the ocean. And the specific ones that we were looking at were Thalassioceras udanana, THAPS, Phaeodactylum tricornutum, or Pheo, and Fragilariopsis cylindrus, or FRAG.
So why are diatoms important? Diatoms are responsible for 40% of marine primary productivity, and they play a huge role in sequestering carbon and feeding the ecosystem and also producing oxygen. So any shift in the diatom population, since they're kind of like at the bottom of the food chain, is going to affect all the other like organisms in the ocean ecosystem. So it's really important to understand what the diatoms are going to be looking like in the future as the ocean acidifies.
So like I said earlier, we are trying to predict like the rise and fall of diatom species. And the way that we've been looking at this so far is through this one gene. So Jake found a high correlation between diatom resilience and this one specific gene, or it's an antiporter. So in THAP specifically. So he noticed that like expression of this gene increases as and when the diatom is in high carbon and it's becoming more resilient. So we were trying to see is, do other diatom species have this gene, and is this going to lead to an increase in resilience for these diatoms also? Because we're thinking that maybe this gene could potentially be used as a biomarker for diatom resilience, and it could help us predict what the ocean's going to look like, which diatoms are going to be more prominent. Right now, it's Chaetoceras and Thalassiocera, but that like ranking of which diatoms are most common could definitely change based on whether or not those diatoms have this antiporter, which could potentially be a biomarker.
So what is this gene that we've been looking at? It's the sodium potassium proton antiporter in THAPS. And we've seen that it's upregulated in high carbon conditions on a diel cycle, which means it's expressed the most in high carbon and during the night, as you can see in this chart here. The blue is the low carbon expression, and then the red is the high carbon expression. And we can also see that it's located on the plasmid membrane. If you see this like green, that's the antiporter, and we've seen that it's expressed on the plasmid membrane, and that means that we can hypothesize that it maintains the pH homeostasis across the plasmid membrane, which is important in high carbon conditions when the plastid is performing photosynthesis and taking in CO2 through this membrane.
So our project was essentially to optimize a protocol to be able to measure this gene and its expression in THAPS and also in its orthologs FRAG and Pheo using RT-qPCR instead of RNA sequencing, so that we can reduce the cost of being able to measure this gene expression. And our hypothesis was that we predict that having this antiporter will allow species of diatoms that have it to be more resilient and more prominent in high carbon conditions.
So our process, we began growing cells. So we grew cells from 3 different species of diatoms, THAPS, FRAG, and Pheo, and then we extracted their DNA. And then we also had to make primers for PCR and find orthologs of this antiporter in FRAG and FAO. And then we had to validate our primers on the DNA that we extracted, and then we had to extract RNA on cells and validate primers on this RNA. And then our final step is this reverse transcription quantitative PCR, which we did for the first time yesterday, but we're hoping to do it more in this coming week.
So the first step in this project was kind of for us to understand diatoms and kind of learn what we would need to do to kind of be able to run these experiments. So we set up growing thaps in these large bioreactors for the first time ever, just so we could learn, how do we sample? How do we cell count? How do we measure quantum yield, fluorescence, and all of these other things? And it also gave us an opportunity to learn how to code for the first time, which Beatrix and I had never done before. So we made these graphs as we were growing them just to track that they were growing normally. This just helped us monitor the conditions, make sure nothing weird was happening, so that we could, when we were doing our PCR and testing whether it was working, we could make sure that our diatoms were growing in good, normal conditions.
So our next step was primer design. And so we needed to design primers in order to run PCR, which is when we make a bunch of copies of a gene, and so we can end up testing the expression of these specific genes. And we have 3 genes for THAPS that we needed to find primers for. The first one was the antiporter, and then the second one was an internal reference gene. And this is a gene that should have similar expression levels across different environments. So these genes should have the same expression in high and low carbon. And then the third one is a carbonic anhydrase. And this is a gene that we know should be less expressed in high carbon conditions, which is inversely related to the antiporter, which should be more expressed in high carbon conditions. And so we did this NCBI primer blast, and we created a bunch of primers. You can see these pictures. We have many primers for all these different genes that we needed to test. And then our next step was finding orthologs of the antiporter. And so we used ensemble protists, and we entered in the sequence of the gene of the antiporter. And then we wanted to find genes in other species of diatoms that had similar sequences. And so we found these 2 genes in FAO and FRAG. And the gene in FAO is interesting because we already know that it has this dial cycle expression, and it's more expressed at night, which is similar to the gene, the antiporter in THAPS. So that was kind of a promising feature of this FAO antiporter.
I just want to clarify that there is orthologs in other organisms. We just chose these ones because we already had the, bless you, cultures for them. So the next thing that we did was we grew FAO so that we could extract the DNA to actually be able to run the PCR on it. And as you can see, we were bubbling the carbon through it so we could, get our high and low carbon conditions correct. So we would bubble more carbon through in high carbon and less in low carbon. And you can see through our graphs that FAO was growing pretty well. It had good quantum yield, good fluorescence. One of the characteristics of FAO is that it grows, it multiplies very, very quickly. So you can see that the growth was very sharp. The next thing that we grew was FRAG, which did not go very well. FRAG is an Arctic diatom, so it likes to grow at 4 degrees Celsius, and we tried to grow it at 18 degrees Celsius because we did not have carbon pumps that for the high carbon conditions in the cold room. We hypothesized that if we put it in an increased temperature, it might multiply quicker, but that was not the case. As you can see, the FRAG died and the quantum yield was 0. So it didn't really go amazingly, but we tried again in the cold room, and then the cold room broke. It went from 4 degrees to 11, and the FRAG died again. So we didn't really have any FRAG DNA to extract off of, but thankfully Chris gave us some cultures, and we were actually able to do our experiments on FRAG despite, the setbacks. So the next thing that we did was our DNA extractions. So the DNA extraction, we were able to use the DNA that we created on the PCR. However, since it was, I want to say, our second time doing it, we did not end up with very high quality DNA. So that did lead to us having some issues with our gels. in the future, which you guys will see. But it was a pretty cool experiment. We got DNA extractions make a bunch of cool colors, so that was nice to see. So now we're explaining the PCR and gel process. That's a video of me doing a gel. But essentially, like Beatrix mentioned earlier, a PCR will make a lot of copies of this one specific gene that we want by making primers. Primers tell the PCR kind of where to stop and where to start when they're making that one copy. And then the gel kind of shows us if it works. So we'll take that one gene that we copied through the PCR and we'll put it in an agarose gel, which is what I'm doing right now, after we've dyed it, and then we'll run an electrical current through it. And then based on the size of that gene, it'll travel to a certain spot in the gel. So the smaller it is, the further it will travel. So when we can measure like if they're in the right spot by putting it next to a ladder that has like predetermined spots that it'll go to, so we can see, are they in the right spot? Is the band clear enough? And like, did it work?
So then we began our PCR process, and it did not go so well at first. As you can see, here are some of our failed gels, and it actually took 6 gels before we could get a good gel. At first we had a ladder in every single well, and then we saw just streaking, then we saw nothing. So what did we learn? Each time we improved our process and we began to increase the amount of DNA, we increased the amount of primers, we tried new ladders, we redid DNA extractions, we got fresh reagents, and each time we modified our protocol to make sure that we weren't making any mistakes along the way, and we've added little like check boxes and stuff. So then finally, we had a successful gel. We were really excited. It was a big day. And so this gel was exciting because we tested our anti-Porter primer for our FAO, our anti-Porter primer for our frag, and then 2 anti-Porter primers for our FAPS. And each of them worked, as you can see from this clear band. So that was really exciting. And then we just, once again, checked more of our primers, and we found that we had actually 2 working anti-Porter primers for FAO, and then all these other ones that worked, including our internal reference primer, which was good. And you can see almost all of our primers worked. And so then we were ready to move on to our next step.
So our next step was an RNA extraction. So this is actually the specific reason why we were growing the cells, because we wanted, for the RNA extraction, we need the cell to go through the specific conditions so we can see, like, is it expressing those genes in those conditions? So obviously we couldn't do that for frag, but we did have it for FAO and FAPS, and then for frag we just tested it on like a standard low carbon culture. So we use the RNA to measure the expression, but you can't do a PCR on an RNA. So we had to make cDNA off of our RNA. We did, again, struggle a little bit with the RNA extraction. So we did, our RNA was a little low quality, which again led us to run into some issues with our gels, but it did end up working, as you guys will see.
So now we're validating our primers on our RNA, which have been turned into cDNA. And this was also a process but we ended up getting a good band for our anti-Porter primer, our internal reference primer, our carbonic anhydrase primer, and then also for our potential anti-Porter primer for our FAO. So we had these primers checked off, and we moved on to our next step once again.
So our next step was RT-qPCR, which is reverse transcription quantitative PCR. So this part was essentially to actually measure the expression of the gene. Previously, we were just testing if our primers even worked to measure expression, and now we're actually measuring the expression. So we did this yesterday afternoon. So we tested it. We tested our THAPS anti-Porter, our THAPS carbonic anhydrase, and our THAPS internal reference, as well as the FAO anti-Porter. So we can see that our primers worked for THAPS. So we can see that we were measuring the THAPS expression as the PCR is making copies of that gel. We can see that it's doing the same for the carbonic anhydrase and for the internal reference. So since it's, as you guys know, because you guys took algebra, if an exponential equation starts with like a higher initial value, it's going to have like a higher slope and it's going to increase a lot faster. So we can see obviously that the highest expression of all of the genes that we measured was for our antiporter, which is good. So we know it's being expressed. The one unusual thing that we did notice was that for our antiporter, it was being expressed more in low carbon rather than high carbon, which is the opposite of what we've been seeing so far. However, the carbonic anhydrous and the internal reference were both good. They were expressing as we expected. The carbonic anhydrous had higher expression in low carbon rather than high carbon, and the internal reference did have like roughly the same expression in both. Something we did notice was that low carbon expression was higher than high carbon in all three of our graphs. So we were thinking that maybe we may have measured the concentration of our DNA of our cDNA for low carbon incorrectly and may have accidentally added too much, considering it's consistent across all of our graphs. So we are going to be doing this again next week just to see if that was the issue. And then for FAO, as you can see, it didn't really do anything. However, you can see it's turning up a little bit at the end. We didn't have time to like fully run this to the end yesterday. So we were thinking that maybe if we give it more cycles and we run it more until it starts, flattening out, that we could see some expression for the FAO antiporter as well. It's just not being expressed as much as it was for THAPS. So there is potential here. Sure.
Okay, so in conclusion, we were trying to optimize a protocol to measure the expression of the antiporter in high versus low carbon conditions in Thalassiocera pseudonana and its orthologs Phaeodactylum, Tricornutum, and Fragilariopsis cylindrus. And so we didn't quite finish the protocol, but we had some successes. We found a working internal reference and antiporter primer for THAPS, and we also potentially found a working potential antiporter primer for FAO. So we want to be able to further test the expression of these different genes so that we can know, like, does FAO, does FRAG have this antiporter gene, and will that help it thrive more in future high carbon conditions in the ocean? And we also would like to do some successful reverse transcription qPCRs.
Next week, hopefully.
Next week.
So some of our next steps for doing this more next week and also just in the future in general is that we would redo our RNA extractions so that we can get better quality RNA. Beatrix and I both need some practice with that. And then we'll make more cDNA for that and start testing this again, see if we can get better bands, better results. And also do just like more repetitions of this since we don't have that many like repetitions of this experiment yet. And then we would also like to find orthologs in other species such as Nitzschia and Cattosaurus to see how those are going to fare in the future. Cattosaurus is the most, it has the largest population of diatoms right now. So it'll be interesting to see if Cattosaurus has the antiporter and if it's going to help it or not. And then we'd also like to run the RT-qPCR on THAPS, FAO, and FRAG with hopefully successful primers. We also like to test on the orthologs if having this antiporter will increase its resilience the way that it does for THAPS. And hopefully we will be able to make predictions about which diatoms will be more prominent in the future based off these results. So for the last few things we want to talk about is our intern experience here. So part of the high school intern program is being a part of the Systems Education Experience program, wonderfully run by Claudia and Sarah. So thank you so much for letting us be a part of this opportunity. So we got to do a lot of cool stuff. We got to interview a lot of cool scientists to kind of see ourselves in the future, like where we would like to be, kind of figure out that path. So we got to interview a lot of cool people. For a couple interviews, we decided to do some fun interviews. So we did Google autocomplete interviews, if you guys have ever seen those. If you haven't, you should definitely watch them. We also got the chance to make a website to document our journey with the other interns. We are in a cohort of 9 high school interns, which has also been really fun. And then we also got to participate in Leads, which has kind of helped us acclimate to what it's like being in a science workspace and overcoming challenges and frustrations with experiments and learning how to work together and be a leader. So that's been really fun so far.
So alongside all of this hard work that we've been doing, we've also been having a lot of fun just working in the lab together, exploring South Lake Union, getting mochi nuts, hanging out with all the other cool people in the lab. And we also enjoy making TikToks. Our intern cohort is going to be starting a TikTok account actually. And so here's one of the ones that we have made, which is kind of like a summary. We filmed ourselves for a short clip every few days in our time here at ISB. And we also used an audio from the TV show Community, if any of you guys have ever seen it. So,
Oh, wait, before we play it, the audio was turned up very loud for Xochi's video because she has kind of a quiet voice, and our video is kind of loud, so do we turn it off from the side panel? Yeah. Okay. Okay.
Troy and Abed in the morning, 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 Troy and Abed in stop motion, Troy and Abed in the morning, Troy and Abed's new apartment, evil Troy and evil Abed, Troy and Abed sewn together, Troy and Abed being normal, Troy and Abed in the morning,
Troy and Abed and Annie in the morning.
Troy and Abed in the morning, nice. Troy and Abed in the morning, nice. Troy and Abed shooting lava.
Okay, so we just want to say thank you to all of the wonderful people that have helped us through this experience. So thank you so much to Jake and Chris for mentoring us in and outside of the lab. We've had so much fun working with you guys, and we're really grateful. Thank you so much to Claudia and Sarah for making this experience really fun and welcoming and matching us up as partners. You guys did so good on that. And thank you to the rest of the Beliga Lab and the education team and just everybody who is here to support us and make us feel welcome, especially the undergrad interns. They were all super nice. And yeah, thank you so much.